Okay. So let's wait another minute and then we'll start. All right. Okay, guys, let's start. So we're going to continue with the sequence of lecture on recurrent neural networks, but we're going to look at it from a slightly different perspective today. A recurrent neural network takes in a series of inputs and produces a series of outputs. So effectively what it's doing is converting one sequence, a sequence x1 through xn goes in, into a different sequence. Y1 through ym comes out. And then once you begin thinking of it as a transaction from one sequence to the other, then perspectives can change. So speech recognition, for instance, speech goes in, a word sequence comes out, or in machine translation, one word sequence goes in, a word sequence in a different language comes out. But then you can also have things like a dialogue system where a user's statement comes in and the system response goes out, or in a question answering system where a question comes in and the answer goes out. Now, when you see it that way, you realize that the length of the input, the number of symbols or the number of vectors in the input doesn't have to be anything like the number of vectors in the output, the number of entries in the output. So in speech recognition, for instance, you could be speaking for 10 seconds, which would be something like 1,000 vectors going in. It may just recognize 40 words. So here's the general model. It's a sequence model. A sequence goes in and a sequence comes out. And now you can have different versions of it. The two basic versions are one where there's some kind of order synchrony between the input and the output. Specifically in speech recognition, we saw that notion of a time synchrony. You don't have one symbol on the output for every symbol that goes in, but then you do have order alignment, meaning the portion of the input that corresponds to the first word comes before the portion of the input that corresponds to the second word. Now we can even have the second version where you don't even have that kind of correspondence between the input and the output. For example, if you were doing machine translation and you're trying to translate from English to German, I ate an apple would go in, ich habe einen Apfel gegessen comes out. If you look at the correspondence, ate is the second word here. Gegessen is the last word in German. On the other hand, it's actually this one word ate splits into two. It becomes habe gegessen. So it actually sort of becomes two different portions of the output, which are separated by other symbols. So there's no order correspondence between the two. Or you can even have something like this in a dialogue system. My screen is blank and the system can respond, please check if your computer is plugged in. There is no apparent relationship between what goes in and what comes out. But all of these are sequence to sequence transduction problems. And this is the kind of problem that we've been focusing on. So we'll continue to focus on this, where you have order correspondence between the input and the output. So in this case, somebody's playing music. Can you shut it off? Guys, you shouldn't be listening to music when you're listening to a lecture. So this is now here's the kind of problem that we're looking at. You have a sequence of inputs coming in, you have outputs coming out intermittently. Then they're not time synchronous, but they are aligned to one another because the segment of the input that corresponds to any symbol in the output, those segments occur in the same order as the output symbols themselves, like in speech recognition. So the problems we saw here, the outputs are intermittent, right? And we don't know a priori where the outputs must be produced. So how do we perform inference on such a model? Number one. And number two, how do we train such models? We sort of partially addressed how to perform inference on such models. We did that using a greedy decode. So we'll look at how to train such models. And we saw in the last class that if my training data had alignment information, basically if it had information about which input instance corresponded to each of the outputs, then you could indeed compute a divergence with respect of between the outputs at those times and the target outputs, or even replicate the outputs and the target outputs over the entire segment corresponding to each output, and then use this divergence to train the model. Okay. So just give me a second. So this we saw. Now, there's one key factor over here that you must keep track of because this matters. And that is that if we are using the Kullback-Leibler divergence as our divergence measure, then the divergence at any time is, wait a minute. So the divergence at any time ends up being simply the negative of the log of the probability assigned to the target symbol at that time by the network. And so the overall divergence is simply the next sum over all time of the negative of the log probabilities assigned to the target symbols at each time by the network. So just remember this, right? So here's our divergence again. If I'm using the Kullback-Leibler divergence, again, if I'm given the alignment, so I'm told exactly where each output occurs, then remember, we can actually express an alignment by repeating the symbol through the segment that it represents. So then we can define our divergence between our aligned time synchronous sequence and the output of the network, and this just ends up being the negative of the sum over all time of the log of the probability assigned to the target symbol at each time. And if I take the derivative of this divergence with respect to any particular output, that is simply going to be a bunch of zeros. And because at any particular output, the divergence depends on the log of the probability of the target symbol at that time, you're going to have just one non-zero entry in this divergence, and that's going to correspond to the target symbol, and the entry is going to be -1 over the probability assigned to the target symbol. Right. So this is all the old stuff from the last class. Everybody with me so far? So I just see one yes. Okay, we're going to build on this. It's going to go up really fast, right? Now, the problem occurs when the alignment is not provided. If only the sequence of output symbols is provided, but timing information is not given. In that case, first, we're going to use two factors. The first is that although the alignment basically tells you which times the output occurs, you can also represent the alignment by expanding it by repeating each symbol over the entire segment that it corresponds to. So an alignment is basically an expansion of this order synchronous time symbol sequence, so that it's now as long as the input itself. Again, you'll remember this from the last class. And so our one solution was to guess the initial alignment for every training instance, then train your models using the guessed alignment, then use this trained model to realign all of your training instances with using the model, and then use the updated alignment to go back and train the model. So this was the Viterbi training procedure. And now we have a problem. Wait, this is the wrong poll, guys. Hang on. Yeah, okay. There you go. It's amazing that you began answering the wrong poll without realizing it.
That's on me, my bad.
It's an easy question. So 10 seconds. All right, let me stop the poll. And share the results. So here's the result of the poll. We saw this. Viterbi training explicitly estimates the alignment of each training instance and computes the divergence for the estimated alignment. So this means that at each iteration, once you're going to use the current models to realign the compressed symbol sequence against the input for each training instance. So both statements are true. The problem with this approach we saw was that it's heavily dependent on the initial alignment. And if the initial alignment is poor, you're going to end up with poor local optima and bad models. So the alternate solution we claimed in the last class was to not commit to an alignment in any pass. So how can we do this? We're going to consider all possible alignments. And to do that, first, let's go back and look at how we tried to align the compressed symbol sequence to the input, right? So if you had this symbol sequence, BFE, and you had the input, remember, we just processed the input using the network. It gave you the output probability table at each time. Then you pulled out the B row and put it on top. Then you pulled out the E row and put it in second. Then you pulled out the F row and put it in third. And then you pull out the E row again, which is this guy, and put it in a second time. And this was your reordered probability table. And then on this reordered probability table, we try to find the best path from the top left corner to the bottom right corner using the Viterbi algorithm. And that gave us a guess for the alignment of the symbol sequence to the input. And then on this most likely alignment, you could now compute a divergence, which is going to be the sum over all time of the negative of the log of the probability assigned to the aligned symbol at each time. And this was the divergence we were trying to minimize, right? Now, the problem with this approach, or the potential problem with this approach, is that we are committing, let me use this blank space here, we are committing to a single alignment through the model, right? And that may be wrong, that may be very wrong, and you're going to get stuck in a bad place. So what is the alternative? Now, if you look at this model, there are many different ways of aligning the input to the symbol sequence, right? There are many different ways of aligning it. Now, every single alignment has a probability. Does anybody remember what the probability of an alignment was using this table?
It's the product. It's the product.
It's the product of all of the probabilities, right? So if I consider every single alignment, every alignment, the A1, the AI is going to be the product over time of all the probabilities of all the symbols. So instead of considering just one symbol sequence, let me do something. I will consider every possible alignment. And every possible alignment is going to give me a divergence for the alignment, right? But then I will multiply that by the probability of the alignment and sum over all alignments. Is this equation making sense, guys? It's making, right? So this is what I'm going to use, but hang on. Suppose I sum the probabilities of all of the alignments of this through this table. Is the sum of all of those probabilities going to be 1? Anyone? So what is it going to be? It turns out that that is going to be the probability of the symbol sequence as computed by the model, right? And so when I just weight by the probability of the divergence over here, that's not really a weighted sum. So I'm going to have to divide on the outside by the sum of the probabilities of all the alignments. The sum of the probabilities of all the alignments is going to give me the total probability of the sequence. The probability of an individual alignment divided by the sum over all of the alignments gives me the conditional probability of that alignment. Basically, it's the probability that given that this is the symbol sequence, it is the probability that this could have been the valid alignment, right? So that's the posterior probability of the alignment. Did that even make sense, or was it gobbledygook? Someone help me here. I'm saying that the probability of an alignment given the symbol sequence is going to be the probability of the alignment, which is the product of all of these symbols, divided by the probability of the symbol sequence, which is the sum of the probabilities of all the alignments, right? This term is what I'm going to be weighting the divergence of each alignment by, and then I'll sum over all of the alignments. That gives me, what does that give me? Anybody want to tell me? What is that? That's going to give me the expected divergence over all possible alignments. That making sense to everybody? Right? Anybody who didn't get that? Because this is what we're going to be working off of. Anyone with questions? No. Okay. I'm assuming that everybody got it. So Arisema, what was the yeah?
Can you just repeat it one more time?
Sure, no problem, right? So instead of committing to just one alignment, right? I'm going to look at this. Every alignment has a probability, right?
Yeah.
So if I look at all of the alignments, there's a probability distribution over all alignments, correct?
Yes.
Okay. And so what I will do is I will compute the divergence for each alignment and weight it by the probability of that alignment.
Yes.
That's going to be the expected divergence over all alignments, correct?
Yeah. Yeah.
And for any given alignment, the divergence is simply the negative of the sum over all time of the log probability of all of the symbols in that alignment, right? Everybody with me here? Any questions, guys? So Medan, what was your question?
That was my question.
Did I answer it? Okay, fine.
Yes.
Okay.
Yes. Yeah.
So, Elias, so here's what we're going to do. The most likely alignment, what was the most likely alignment, Ame? That gave you the Viterbi, right? So we don't want to do that. We want to average over all alignments, right? And so here's what happens. Before I say anything happens, you get a poll. Let's get the next poll. Yes, that's an owl. I should put the parentheses or maybe draw the picture of an owl. Nathan will see why it's not going to be computationally expensive. It's going to be very simple, right? But 10 seconds, guys. All right, let me stop this. Oh, okay. And Paul, share results. Actually, let me not share the results. Let me show you the answers directly. And so the answers are these. That when you train without alignment, basically, if you consider all possible alignments, then you're computing the average divergence over all possible alignments of the label sequence to the input, right? It doesn't require explicit alignment estimation of the alignment anymore because you're considering all possible alignments. Now, so Unjay, this is not really EM. We'll see what happens next, right? But it's similar to EM. Now, how do we go about doing this? Remember, we want to compute the expected divergence over all alignments. But the divergence for any individual alignment was simply the negative of the sum over all time of the log probability of the aligned symbol at each time. But then the summation is a linear operation, so I can take the expectation inside. And when I take the expectation inside, this just becomes the sum over all time of the expected log probability of the symbols at each time. So what is this crazy thing? What is this expectation? This expectation is simply going to be is the expectation of all of the symbols in any column in the kth column of the table. It's going to be the sum over all symbols of the posterior probability of the symbol times the log probability assigned to the symbol in that table. Now, what does this posterior probability mean? Why is this?
I have a small question here. Sorry.
Yeah,
X is the alignment and S is the symbol, right?
Which is X is the input.
Posterior.
X is the input.
X is the input. Okay, and S is the symbols.
S is the symbol sequence, right?
Okay, thank you.
So now, so what is this term over here? This term says if I choose a random alignment through this table, right? Through this graph, by drawing from the probability distribution of over all alignments. If I randomly choose an alignment, what is the probability that that alignment goes through this node in the graph? That's what this means. And so this term over here is the probability that a random alignment will go through this node times the log probability of this node plus the probability that a random alignment will go through this node times the log probability of that node plus the probability that a random alignment goes through this node times the log probability of that node, and the same thing for this guy. So this summation over here is basically summing through the column, and in the column for each node it multiplies the probability that a randomly drawn alignment will go through that node. It multiplies that probability by the log probability of the node itself. So is everybody getting this formula over here?
Wait, sorry, could you explain that again real quick?
So this
multiplying the columns.
So this inner term over here, right? You're taking the expectation of the log probability of the nodes, right? So what does it mean? Consider any time t. That is the sum over, so I'm saying, what is the expected log probability of the aligned symbol at that time? That's going to be the probability of each node multiplied by the log probability in the node, right? And what do I mean by the probability of each node? It is the probability that if I randomly choose an alignment, it's the probability that a randomly chosen alignment will go through that node.
So K equals 4 in this case, right?
K is 4 in this case.
Okay, thank you.
Right, so because you're summing over all. Any other questions?
Professor, so when we computed the average, the weight average of the divergence, are we only need to choose the alignment from the vertical graph, or don't consider the vertical graph and choose them randomly from the whole graph?
Okay, hang on, right? So it's a good question. Hold your soul and peace a bit. So what I'm saying, so let's focus on this equation again. We want to compute the expected divergence for each time. You want to sum this over all time. The negative of that is the overall divergence that we are computing that we want to minimize, right? And so
Yeah.
what is the missing term over here? The missing term is this guy. The probability of aligning a specific symbol B to the specific time t, correct? That's what this guy is, right? If I have it for every one of these guys, then I can compute the divergence contribution of this column, right?
Yes.
And so what exactly is that probability? That probability, let's consider this node over here. The probability that a randomly chosen alignment will go through this node is the total probability of the entire subgraph that goes through this node. Well, it's proportional to the total probability of the entire subgraph that goes through this node. Does that make sense?
Yes.
Right. Any questions here, guys? This is key. This is what we're going to be working off of. Questions? How do we calculate it? That's what I'm going to tell you, right? But is this concept making sense? That the probability of a node, of that a randomly chosen alignment will go through this node, is the total probability of all paths that go through this node, which is the total probability of the entire subgraph that goes through this node, right? And
professors,
yeah.
Sorry. So for example, if we want to compute the expectation of the t equal to zeros, then we should only consider the y0b instead, and do not consider the last three y0e and y0phi and also y0e, right?
Because they have zero probability, right? You know, you can ignore the fact, you can just treat everything the same. But yes, yeah, in this case, yeah, in this case, these guys would not be considered, right?
I see.
Or you can just say, we'll see how the whole thing works out. Okay, just bear with me. But so this pink subgraph is the subgraph whose probability we want to compute. Correct? We're going to compute it using something called the forward-backward algorithm. Now, what is the forward-backward algorithm? This pink subgraph has two subgraphs. This the graph in pink, in turn, has two subgraphs, right? It's the portion of the graph that's leading from the beginning to this point, right? And the portion of the graph that goes out of this point to the end, but not including this node itself. So does everybody see how this graph has two distinct portions? Right? So now, if I could compute the probability of this graph and compute the probability of this graph, and I multiply the two, then I should get the probability of the entire pink graph. Correct? Now, if I want to draw this, if I want to write the math, I will have to say the probability of the pink graph is going to be the probability of, I'll call the left region the blue graph, times the probability of the red graph, which is the region to the right, given the blue graph, right? Because this pink graph is red, comma blue. Is this equation making sense, guys? This is just Bayes' rule, right? So here's what happened. This, you want to have the probability of this graph times the probability of this second graph conditioned on the first graph. this conditioning can be a mess because, what does it mean to condition things in this manner? It turns out it doesn't mean anything. In this particular case, we have something called conditional independence. What is the conditional independence? What it means is that if I give you the input X, so let's go all the way back here to my network. If I can have a picture of it. Do I have my picture of it? Okay. Right. So now look at this. If I give you this input X, right, then the computation of all of these H's is deterministic, correct? You agree?
Yes.
Okay. So that means the probability that you compute for any symbol over here is not influenced by the probability that you compute for any symbol over here. Meaning, for example, if I were to randomly choose a symbol over here and say that the alignment at this time is the symbol S, that will have no bearing whatsoever on what symbol I will choose from this distribution, correct? Because these two probability distributions were computed without considering the specific alignment at this time. Does that make sense? Meaning, if I chose, because this computation of this probability table is deterministic, right? And because the computation of the probability table is deterministic, what it means is that all of these probabilities, these figures are a mess, but all of these probabilities over here, they're already computed. There's nothing more to compute. So if I randomly say that I'm going to align this symbol over here to my first input, this fact does not modify the probabilities you compute at this time, does it? The alignment happens after this computation is performed, right? This table is computed before the alignment, right? So if I decide that I'm going to be aligning the first symbol to this guy, it does not affect the probabilities I compute at this time. They are independent, right? It may affect something that happens up here, but the actual probabilities computed are not influenced by what symbol I aligned at this time. So that means that the probabilities computed at each time are what are said to be conditionally independent. They're conditioned on the input, meaning once I give you the input, the H's are deterministic. And because the H's are deterministic, the probability distributions at each time do not depend on one another. And so they're conditionally independent. What that means from our perspective is that the probability of all paths in this portion of the graph do not in any manner depend on how you aligned the initial portion of the graph. Is that making sense? So regardless of whether I align the initial portion like this or like this or like this, the total probability of this portion of the graph remains the same, right? So that means that over here, instead of saying P of blue and P of red given blue, I can just write P of blue and P of red. Making sense, guys?
Yes.
Perfect. Okay. So that's what we're going to do, right? We're going to say the probability of all paths that go through this node is going to be the probability of the red graph, which is this first term, times the probability of this blue graph, which is the second term. This blue graph is the graph of all nodes that succeed this node. And the red graph, all paths that succeed this node. And the red graph is the total probability of all paths that end at this node, right? I'm going to call this first term alpha t, or I'm going to call it the forward probability, which is the probability of the pink graph. I'm going to call the probability of the blue graph beta tr. R represents the rth row, right? So This is alpha TR, which is the total probability of all paths ending at symbol, the arc symbol at time t. And I'll call that the forward probability. Beta TR is the total probability of all paths going out of the symbol arc symbol at time t, which is the probability of the blue graph, right? So if I know how to compute these two guys, I know how to compute the total probability of the entire graph. So let's try to figure out how to compute this first probability first, right? The forward probability. The forward probability is the total probability of this graph, right? Everyone with me?
Yeah.
Okay. But then if you consider this node, there are only two ways to come to this node. You can either come from here or you can come from here, correct? So the total probability of all paths going into this node over here is going to be either the total probability of all paths arriving here times the extension, which is the probability of this node, or the total probability of all paths arriving at this node here times the probability of extending it to this node. That makes sense?
Yeah, Professor.
Yes.
Right. I'd like to see some hands raised. Does that make sense? Right. Okay. So I'm seeing some hands. All right. Okay. So now that's good. Now, so I can say in other words that alpha TR is the sum over all parents of this node of the total probability of the subgraph ending at the parent times the probability of this node itself, right? But what is the total probability of all paths ending at the parent? Anyone want to tell me what that is?
There's only one path.
In this case, but what is the total, or what is this guy, right?
Sum
What is the
over all possible paths.
But again, in terms of the symbols that we've just explained, what would that be? If alpha 3e is the total probability of all paths ending at symbol E at time 3, right? What is the total probability?
Alpha 2b.
That's alpha 2e, right? And what about this guy? Alpha 2b, right? So therefore, the total probability of all paths ending at ye3 is simply alpha 2b times ye3. ye3 is the probability assigned to symbol E at time 3 plus the total probability, total probability. This is alpha 2e times y e3. So is this equation making sense, guys?
Yes.
Yes.
Rest of you, okay? Or this generalization of it, is it making sense? Right, very simple, right? And so that gives us our algorithm. It's very trivial. Alpha TR for the rth row at time t is the sum over all parents of that node of the alphas, the product of the alpha for the parent times the probability of the node itself, right? In fact, I can write this guy out here, and it's simply going to be the probability of the node times the sum of the alphas for all of the parents of the node. That making sense to everybody?
Yes.
Yeah.
And so that gives you, so here's the, in our case, each node has only two parents. So alpha TR is going to be the sum of alpha t minus 1 r, which is this guy, and alpha t minus 1 r minus 1, the previous node, right? The previous time and the previous row. The sum of those two alphas times the node probability. So this is making sense again, everyone?
Yes.
Perfect, right? And so now I have my algorithm. Okay, here's what I'm going to say. The total probability of all paths that go through this node is simply going to be y0 as 0, right? I know that paths are not allowed to go through these nodes. So for the rest of them, the alphas, alpha 0 r is going to be 0 for all of the rest of these guys. For this node alone, it's going to be y0 b. Was there a question? No. Okay. So once I do this, yeah. Was there a question? No. So now I can compute my alphas for all of the nodes in the first column. 4 computations, right? Then I can go left to right. So this is my alphas for the first column. Then using the alphas for the first column, I can just use my formula, which says that for each node, I can just go down this column. For each node, I'm going to sum the alphas of both parents, of all parents of the node. For the top node, there's going to be only one parent. For the rest of them, they're going to be 2 parents. And then I'm going to multiply the sum of the alphas for the parents by the probability of the node itself. So I can compute the alphas for all of these nodes. Then I can go to the next time, and then I can compute the alphas using the same formula for all of these nodes, and these nodes, and these nodes, till I compute the alphas for every node in the graph. This makes sense?
Yes.
Right? And how expensive is it? If you have k symbols, if you have t time instance, then you're going to be going through kt nodes. And for each of these kt nodes, you're only considering 2 parents, right? In this case. So you're going to have the total computation is 2 kt to compute all of the alphas. Right? Everyone with me?
Yes.
Right? Very easy. Yeah. Was there a question? No. Okay. So
Professor.
yeah,
Professor,
go ahead.
can you go back to the slide?
Yeah.
So why are we considering one before?
Pardon?
Yeah.
Pardon?
What? Hello.
Yeah.
Yes. So why are we considering the nodes that we are not considering, or that are not part of the path? For example, Y7B is not part of the path, so you were considering it. So
Here's what happens, right? It doesn't matter. You're going to be computing alphas for all of these guys. It doesn't matter. You're just simplifying the code. You're just going to be, do you want to be, see, you don't want to keep track of too many things about the graph, right? So long as you initialize these alphas to 0, you can just blindly compute all the way to the end. These small number of things, there are a few extra computations. As you will see, they won't really hurt you.
Will they automatically be 0?
They won't be 0. Let's go back. There's more to be done, right? What did we just do? We just computed the alphas, right? We just wait a minute. Where is my? Okay, first, I want to point out something. If you consider the alpha for this bottom node, the alpha for this bottom node is the total probability of all paths from the beginning to this point, correct?
Yes.
What is
Yes.
that? That's simply going to be the probability of the sequence.
Mm-hmm.
All right. Okay. And what we have done so far is to compute
Professor, could you repeat? Could you repeat the previous one? Yeah, this one.
So the alpha over here is basically the total probability of all paths through the graph to this node, right?
Yes.
Which is basically the total probability of the symbol sequence. Basically, the entire path, all paths represent this symbol sequence, right? Every
yeah.
possible way of aligning the symbol sequence to the input.
Correct. Yeah. Got it.
Okay. So
yeah.
So we've computed the alpha for every node in the graph, right? The slides have some pseudocode. Take a look at it. So now I'm going to call this the forward probability. We know how to compute it. So this first term is computed. Let's look at how to compute this second term. Can anybody tell me how you would compute the second term? Anyone want to take a guess?
Just go in the reverse direction.
Exactly. I can do the same thing, right? We're going to be computing this backward problem. I'm going to call this the backward probability. Here's what I will see. What is this backward probability? Beta TR. It is the probability of this exposed subgraph, but not including this node, right?
Yes.
Yeah.
Everybody with me? Right. So just to make life simple, I'm going to include the node in it. Okay. And I'm going to call this beta hat TR, just to make life simple. Okay. So beta hat TR is the probability of the subgraph, including this node. So if I want to have the probability of the graph that doesn't include this node, all I have to do is to take beta hat TR and divide out the probability of the node itself. This making sense?
Yes.
Everybody raise your hands if you got that. Right, very easy. So, okay. So now let's, and then how can I compute the beta hat? This is just like your forward algorithm, right? The total probability of all nodes, all paths from here to here is going to be, this node has only 2 children. So every path from this node either has to go through the green node or it has to go through the red node, right? So the total probability of all paths from this node to the end is the probability of going from here to the green node and then all paths from the green node to the end plus the probability of going from here to the red node and all paths from here to the end, right? Everybody with me?
Yes.
Yes.
And what is the total probability of all paths from here to the end?
Beta for E.
Alpha.
It is also the sum
It's
of
beta-
the
so
Y5
so
and
if
Y.
this guy is beta hat, E3, what is this guy? I mean, if this guy is beta hat E3, what is the total probability of all paths from here to the end?
Beta hat E4.
Beta hat E4, right? And this one is going to be
Beta F.
whatever it is, F
Yeah.
block, right? You get it, right? So this should have been F4, beta hat F4, right? And so beta hat 3E, which is the total probability of all paths from here to the end, is simply going to be YE3 times beta hat E4 plus beta hat F4.
There's a 3 in the formula here.
Yeah, okay. This is a bug. Post this on the slides, and I'll fix this. Right? That's a bug.
Yeah, this is a typo, right?
Yeah, that's a typo. Okay, is this making sense, guys?
Yes.
Very easy, right? And so now I know how to do the same thing. So in general, beta hat TR is going to be the probability of the TRth node times the sum over all successors of that node of the betas for those nodes, beta hats for those nodes, right? So here we go. Here's what we're going to do. We're going to start from the end. For the end, I can compute the beta hat for this guy. The beta hat for this guy is simply going to be YE8, right? This is the total probability of all paths that will start from here and go to the final node, correct? What are the betas for these guys going to be?
0.
Yeah, there's no way of starting from these guys and going here, correct?
Yes.
So there
So
you
the
go.
other one is 1.
No, so I'm saying, remember, we also include, so this is the total probability of the node, so it's YE8, right? All paths starting from here and ending there. That's YE8, correct?
Yeah.
And so that's going to be your initial beta hat. Then you can take a step back and then you can compute the beta hats for all of these guys, where the beta hat for any node is going to be the probability of the node times the sum over all children of the beta hat for the children, right? Correct? That's this formula,
Correct.
right?
Yeah.
And so I can work my way backwards all the way to the beginning. Correct?
Are we
Yes.
allowed to choose YE8 as one, or is it less because there are more symbols than Biffy?
So this is just the raw graph. YE8 is not 1. YE8 is YE8. Remember, we're computing beta hat. Remember? Beta
Yeah,
hat. So,
okay.
right? So again, this was, I want to note the distinction between these guys. The distinction is what we wanted was this, not including the node. But for simple purpose of simplification, we also included the node, and that gave us beta hat, right?
Yeah.
Okay, so YE8 is included. But then after once you've got the beta hats, what you want to do is you want to convert the beta hats to the betas. And to compute convert the beta hats to the betas, it is going to divide by the probability of the node itself, right? Yes, Jinko, you could just flip it and run it through the forward algorithm, except you're going to start from the bottom, right? So you're going to have to flip it up, down, left, right. So
Professor,
yeah.
sorry, can you turn back to the 59?
59, that's a long way back.
Yeah, 15. Oh, sorry. I'm a little bit confused about why is the first P is the subgraph starting at 4E and the second one is subgraph ending at 4F. Shouldn't them be consistent?
I'm not sure I understood your question, right? Oh, this.
I mean, it's the subgraph
No,
starting at
so,
this.
so this should be starting at 4E, and this should be starting.
Oh, thank you.
Thank you. Please post this also on Piazza. These are mistakes
Okay.
that I must fix. Okay.
Okay. Hmm.
Thank you. That's a very good. You caught a few mistakes. Don't forget to post on Piazza, because otherwise I'm going to have those posted ready, right? So
Sure,
we
no
see how to
problem.
do this, and there's pseudocode for doing this, right? So I have the entire code over here. Now that was the backward algorithm. Now here, what did the backward algorithm give us? The backward algorithm gave us the probability of the blue graph, right? And so that is my beta TR. And so now I have computed beta TR for every single node in the graph once I perform the backward algorithm. And so now, if I want to compute the total probability of the subgraph that goes through this node, I just have to multiply alpha TR and beta TR. Correct?
Yes.
Yes.
Everybody with me? Right. Easy, right? But then, what was it I really wanted? I wanted the condition. I said, given that this is the symbol sequence we are trying to align, what is the probability that a randomly chosen alignment goes through this node, right? So it's P of this node given this guy, whereas the product of alpha and beta simply gave you the total probability of all paths going through this node. So to make sure that these four probabilities sum to 1, you have to divide by the sum of alpha beta over the column. Is this making sense?
No.
No. Okay. So the question we asked was, if I align the symbol sequence to the input, right? Given that I'm aligning the symbol sequence to the input, what is the probability that a randomly chosen alignment will go through this node? Correct?
Yeah.
So a randomly chosen alignment must go through one of these 4 nodes, correct?
Oh, yes.
Yeah.
So these 4 must sum to 1, right?
Yeah.
Yeah.
But the product of alpha TR and beta TR will not necessarily sum to 1 across the column. In fact, it won't, right?
Yeah.
Yeah.
So we normalize. That makes sense to everybody?
So basically you are just dividing by the sum to normalize the probability, right?
Exactly, right?
Okay.
And as it
And
turns
so-
out, yeah, and as it turns out, this denominator term is simply going to be the total probability of all paths through the graph. So it's going to be the alpha over here. Okay.
And if you would do the algorithm, but like choosing YE8 to be 1, then you wouldn't have to normalize this.
You would still have to normalize it
Okay.
because the alphas and betas are not, the product of alpha and beta is not going to sum to 1, right?
Yeah, and alpha and beta incorporate the whole alphabet.
Exactly. No, the alpha and beta are going to be
Okay.
incorporating this entire symbol sequence, right?
Okay.
Got it? Yeah. Not the entire alphabet, just the symbol, aligned symbol sequence. And therefore, let me call this the posterior probability, gamma TR. That is the probability of that a random alignment goes through the node. It's going to be alpha TR, beta TR, the product of alpha TR and beta TR normalized. Yeah. And so the divergence that we saw is the negative of the sum over all time of the product of gamma TR at each time and the log of the probability at each time. So is this making sense, guys? Perfect.
Yes.
And so that's it. There's a poll. Let's see, let's pull up the third poll.
I have another small question. Why is it important that we normalize this if the vector is the same for the whole column?
Because you're computing the expectation. If you don't normalize it, oh shit, I have a problem. Let's skip the poll, right? This fourth question, the second question must have come some other place. My mistake, right? Let me stop this poll because I did not actually introduce that other concept. My bad. I make mistakes, obviously. But yeah, so here was the poll. The forward-backward algorithm is used to compute the a posteriori probability of aligning each symbol in the compressed symbol sequence to each input, right? And the probabilities are required to compute the expected divergence across all alignments of the compressed symbol sequence to the input. So this is what we just saw, right? And so if I want to perform gradient descent, I have to take the derivative of this divergence with respect to the probabilities. And I need the derivative of this divergence with respect to the output of the network at each time. But then at each time, the network is actually producing outputs over all possible symbols, right? And you're just picking some subset of these guys over here for this column, right? So what will happen is that the derivatives with respect to these other guys who are not represented here are going to become 0. The derivatives with respect to the guys over here are simply going to be, for any particular symbol, you'll observe that its contribution at that time to the divergence is the log of this probability, which is the log of this guy, times the gamma TR at that time, right? So when I'm going to be taking the derivative of this divergence with respect to this YT. And if you work it out, this derivative, the derivative of the divergence with respect to these YTs must come from this formula at each time. And that is going to be simply, if you take any particular symbol, if over here, for example, the derivative of the divergence with respect to the probability assigned to the symbol A is 0 because A doesn't occur anywhere, right? But if I look at the derivative of the divergence with respect to the probability assigned to symbol E at any time, it's going to be the contribution YE occurs twice in this particular case. So it occurs in multiple columns. So you're going to rows. So you're going to go over all the rows that include the symbol. And it's going to be the derivative of gamma times log Y. So you have one gamma here and a gamma here. with respect to y. And that, of course, the derivative of log y is simply going to be 1 minus 1 over y. There's a minus outside. And is the summation over all the rows that include that symbol of the gammas for that row. Did I confuse you guys, or did this make sense?
I'm confused.
Okay,
It's confusing.
obviously confusing it, right? So I'm not going to finish this lecture, this class and this lecture. I'm going to have to do an extra lecture for you guys. You'll have to bear with me, right? So consider this. What we need is to compute the derivative of this divergence for back propagation with respect to the output of the network at each time, correct?
Yes.
Okay. At each time, the network produces probabilities for all the symbols, right?
Yeah.
Yeah.
Okay. Now consider this guy. If I want to compute the derivative of the divergence with respect to the output of the network at time 3, right? So the derivative of the divergence with respect to all the symbols that are not represented here is going to be 0, because obviously they don't influence the divergence, correct?
Yeah.
Okay. Now consider a symbol like E. E occurs twice over here, right?
Right. Yeah.
Okay. The contribution of E is going to be the gamma at this location times log of the probability of E plus the gamma at this location times the log probability of E, right?
Yes.
Yeah.
Okay. So if I take the derivative of the divergence with respect to the probability of E from log y, the derivative is simply minus 1 over y, right? Because there's a minus over here, correct?
Yeah.
But then you also have this additional thing. It's going to be summation over all the rows which include y of gamma TR, right?
Yes.
Merin, did that make you answer your question?
Yes, it's clear now.
Okay, so that's very easy to compute, not fancy. And so basically, to get the derivative with respect to ye4, I must be summing the contributions of both of these guys. And so the overall derivative of the divergence with respect to the output of the network will have a bunch of zeros corresponding to symbols which are not here. And for the symbols that are here, it's simply going to be minus 1 over the log probability, minus 1 over the probability of the symbol times the sum of the gammas over for all the rows where the symbol happens, right? And so, but then there's the second thing, right? So this guy, if I consider any one location, the derivative is going to be gamma divided by y, right? The derivative of this time, right?
Yeah.
But you also have to consider the derivative of gamma itself, because gamma is also influenced by y, right?
Yes.
Yeah. So this term is easy. It turns out this term is really ugly to compute because gamma includes everything from the future and everything from the past. So when you get something that's really ugly to compute, what do?
Drop it.
You drop it. You come up with some vague mathematical explanation which says it's not necessary and throw it away. And so, yeah, that was a brilliant answer. That's right. So we just throw it away. And we retain only the first term. And you claim this is a maximum likelihood estimate and everybody's happy. So that's what your formula ends up being. And you say it's intuitive, obviously. And so the derivative of the divergence with respect to the probability assigned to any symbol at time t is minus 1 over that probability times the sum over all rows where that symbol occurs of the gamma TR. Obviously, if the symbol never occurs, this term is going to be 0, right? So it's yes, Karan, it's obvious. And it's obvious to most people. And as we know, most people are not most people. Anyways, so this is this clear to everybody?
Yeah.
Okay.
Yes.
Beautiful. And so here's the overall training procedure, right? Given input and output sequences without alignments, you set up a network, typically in many layered LSTM, you initialize all the parameters of the network, could be randomly. Then you compute this. Each training instance gets put through the network, and you get this probability table. And then from the probability table, you compute the reduced probability table for each sequence. And then from the reduced probability table, you construct the graph. You do the forward algorithm and compute the alphas for every node in the graph. You perform the backward and compute the betas for every node in the graph. From the alphas and betas, you can compute the gammas. From the gammas, you can compute the derivative of the divergence with respect to the network output at each time, which is given by this formula here. And now you have the derivative of the divergence with respect to the output of the network at each time. You can just back propagate that further and compute the and train the network. After all, once you get dy over d dive over dyt for every time instant, the rest is just bptt, right? Back propagation through time. Everybody with me so far?
I have a question about the divergence function. Is that this divergence function means that we are feeding all the possible permutation to the divergence function?
All possible alignments.
Yes, all possible alignments.
Correct.
Okay.
Perfect, right?
And here we are only training the model for finding the alignment, but not the language model.
No, because you're computing the derivative of the divergence with respect to the output of the network. An alignment is never ever invoked, correct?
Okay.
You're learning the model. This is now back propagated and you're going to train the model.
Okay.
Right? So sequence to sequence more networks which regularly output symbols can be decoded using Viterbi decoding. They require to can be trained by iterative alignment, but they require alignment, and this alignment is there's something wrong with that first bullet. Okay, but let's go to the third bullet. Training can be performed by iteratively estimating the alignment by Viterbi decoding and time synchronous training. Alternately, it can be performed by optimizing the expected divergence over all possible alignments. Right. So there's a very long chat question. I can't read it. Anyway. So far so good. But then we're missing one key decoding problem. We know how to train the network. We still haven't really figured out how to decode. Remember, suppose when we did the greedy decode, we said that if we just pick the most likely symbol at each time when I'm performing inference, and I began merging it, there's no way for me to know whether a symbol occurred twice or all of them must be merged. Remember? So, for example, if I have a greedy decode of this kind, which looks like so, 3 R's, 4 E's, and a D, should I be compressing it to read or should I be compressing it to read? This information is not available, right? So how do we deal with it? We saw this earlier, correct? So how do we deal with it? For this, to deal with this business, we are going to introduce an extra symbol, who's basically mostly unemployed. It's a jobless, it's got only one job in life, which is to serve to separate discrete versions of a symbol. We're going to call it a blank. And we're going to call it, it's not a space. It's not a space. We're calling it a blank. I'm going to represent it by this hyphen symbol, okay? And so, if I have, for example, so the hyphen is a unique symbol. Remember, when I wanted to decode, what I did was I did a time aligned decode and then I compressed it, right? I just eliminated all repetitions. If I get something of this kind, RR hyphen hyphen RE, what will happen is these hyphens will not just compress and become a single hyphen, they will completely disappear. And so this guy, these two R's are going to get collapsed to an R. These hyphens will disappear. But then because these hyphens separated these first two R's from the second R will remain. And so this is going to become RRE. Similarly, if I were to be compressed, if this were my time aligned output, and if I were to squish it down, these three R's would get merged and I'm going to get an R. These three hyphens are going to get squished, but they're going to disappear because they are nothings, they're do nothing symbols. Then these two E's are going to get compressed and they become an E. These three hyphens get squished out, and then these three D's become a D. Now here, for example, the two R's get compressed, they become an R, there's a hyphen which disappears, there's an E which occurs here, these hyphens disappear. And then these two E's get compressed to an E, and then we have a D, right? So similarly, this guy over here, the two R's get compressed to an R, this hyphen is going to disappear, this R remains, these hyphens get compressed to nothing, these two E's remain, will get compressed to 1, the hyphen disappears, the D stays, and then this one hyphen disappears, and then the two D's become a D. So I'm going to get RREDD. Is the use of the hyphen making sense to you guys?
Yes.
So Menon, the hyphen is just a symbol, just like any other symbol. The only one thing that happens is that when you squish things down, the hyphen doesn't stop at 1, it goes all the way and goes away, right? So can anybody tell me what this guy is going to become?
E D D D.
RREEDD, correct? Perfect. So everybody got it. Beautiful. That's indeed what it becomes, right? So the symbol set.
Professor?
Yeah.
Professor, so I understood the use of hyphen in what you just explained right now, but I'm not able to understand how many hyphens are there between the words and how do we come up
There are
with that?
so here is the point. Remember, if I'm decoding some x1 through xn, right?
Yes.
Correct. When we did the greedy decode, we were just picking one symbol at each time, correct?
Yes.
The most likely symbol. The most likely symbol could also be the hyphen. That's it.
Oh.
Okay.
So the three. So if, for example, in the fifth one, there are three hyphens between R and E.
So this just means that the input over here was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 symbols long.
Okay, so the number of hyphens can vary.
The number of so it's just as, you know, if I want a symbol R, if I want to align a symbol R, the number of times it repeats can be anything, right?
Okay.
So the hyphen is just a symbol like R. The only specialty of the hyphen is that when you compress things, if the hyphen doesn't stay at one hyphen, it compresses and becomes absolutely nothing.
Oh, okay.
Okay.
Okay, yeah.
So, for example, okay, here's, do I have the right? This is the form. Let me ask you this form. Wait. This is the wrong part. It's something is off. Okay, I have the wrong pole. So let's just go with the pole over here. Skip this, right? I seem to have entered rubbish into Zoom. But which are the valid expansions of the character string Billy, right? And you can see BB, II, LLY. Why is this not valid? Why is this not a valid expansion of Billy? Anyone?
There's two
It'll
L's.
be BILY.
This just compresses to Billy, right? What about this guy?
Two
What will
B's.
it
Well,
it'll become B I L L Y, right? What about this one?
BILY.
B I L Y. So, but this one is BILLY, right? So you see how the whole blank thing works. Beautiful. So when the model computes probabilities, the symbol set now has an additional blank in its vocabulary, and it's going to be computing probabilities of all the symbols, including the blank. Okay. And if you were to just do a greedy decode, you might get a greedy decode of this kind, in which case these two are going to get compressed and it becomes a B. These two are going to get compressed and it becomes an E. These two are going to get, these four are going to get compressed and this becomes an F. You get an E, so this became a B feed, right? But suppose this was my greedy decode, then what does this compress to? Anyone? What does this compress to?
It's still the same.
It's still the same. The first blank will go away, right? I'm going to get B, I'm going to get E. These two blanks will disappear. I'm going to get F, I'm going to get E, right? So you can see how this works. What about this guy?
Be double F.
Because this blank is going to disappear. You get a B, you get an E, you get an F. But then you got a blank over here, so you're going to get an F, and then an E. So everybody get what we've been doing?
yes.
Yeah.
Okay, beautiful. So this changes things. I'm going to go a couple of minutes over, and I'm going to have to do another second lecture later today. So this changes things, right? Remember when we didn't have blanks and we were trying to align something, this is how we compose the graph, right? But then if I'm trying to align B phi to my input, actually I sort of changed it. I made it B, E, E, F. This is a horrible example. I've been using it for many years. I keep planning to change it, but the figures are so complex. I don't do it. So suppose I've got beef with two E's, right? If I just composed a graph of this kind for this, what's wrong with this graph? What's wrong with this graph?
You need a hyphen between the two E's.
I need a hyphen between the two E's because any alignment that I'm going to get is going to be of this kind. And it will collapse to simple B, E, F. It's not going to collapse to two E's, right? So what I will need to do is to compose a graph like this. I'm going to need to add a hyphen between every two symbols of this kind. Now remember, a hyphen must occur between repetitions of a symbol. It may or may not occur between two different symbols, right? So to account for that, my graph now ends up looking like this. The first symbol might be either a blank or a B, right? So now a B, a B can be followed by a B, which is to say it's just a simple repetition. Or it can go to a blank, which means that, the symbol is changing. Or it can go to an E because B and E are different symbols. Is this structure making sense? Guys?
Yes.
Yeah.
Okay.
Yeah.
A hyphen can either go to a hyphen or it can go to the next symbol, but it cannot skip. Why can a hyphen not skip? Anyone tell me?
We will lose the I in between.
You lose the symbol that is there in between, correct? And so here is what the structure looks like. Basically, from any node, you're going to have one edge which is horizontal, one to the hyphen, and 1 2 steps down, except For hyphens, you only have these two connections, right? Also, if our symbol over here is the same as the symbol over here, then you're going to have only these two connections. You will not be allowed to skip the hyphen. If you skip the hyphen, then the two E's will get collapsed. So is this graph making sense to everybody?
Yes.
Yeah. With a possible alignment, Amay, right? The way to think about it is in terms of this guy. Remember, I could have, I had an example over here, right? I could or could not have the blank between the E and the fur. Remember? It's a possibility. So we are saying that the first symbol, again, look at this. Here the first symbol was a blank, right? Shubham? So it is possible for the first symbol to be a blank. Here I got B phi, but the first symbol actually aligned to a blank. Make sense? Okay. And so this is how we're going to compute the graph, okay? And observe that the first and the last columns are also allowed to end at initial and final blanks. Skips are permitted across a blank, but only if the symbols on either side are different, because a blank is mandatory between repetitions of a symbol, but not required between distinct symbols. And so we're going to modify our forward algorithm to work off this graph. I actually won't go through the forward algorithm, but basically it's the same algorithm as before. The alpha for any node is going to be the probability of that node multiplied by the sum of the alphas for all of its parents. And specifically, if you have this is written poorly, the clause should come before the thing. If you are in a row which is either a hyphen or a row where the next symbol is also the same symbol, then you'll only have two parents. For other rows like this fur, where the previous symbol is actually not the same as fur itself, you're going to have three parents. You're going to have fur itself, you're going to have the blank before, and you're going to have the symbol to above, and so you'll be summing three alphas. But that's it. So I'm kind of out of time. I'll stop here. Okay, let me stop the recording. Brad, can you stop the recording?